Previously, we examined how to calculate approximate 95% confidence intervals. But what if you want to create a confidence interval that is an 80% or 90% confidence interval? Well, we can calculate confidence intervals of any size, 50, 80, 90, 95%, 99%. Right? Again, we can think of the mean of a random sample. It's just the point estimate for the population mean. It's our single best guess without additional information of the population mean mu. But again, using the concept of the standard error, which is just the population standard deviation divided by the square root of the sample size, that's the standard deviation of the sampling distribution, we can create a confidence interval of any size using a point estimate plus or minus a critical value, which we call Z star, times the standard error. This critical value, or the Z star, it's a number that corresponds to the confidence interval we want. How do we get this value of Z star? If you recall, with 95 approximate confidence intervals, so if we have like 95% confidence intervals that are approximately so, then we use a value of roughly 2 for this critical value of Z star. But for confidence intervals of any size, 80, 90, 95%, how do we get that value of Z star? So let's step back and think about the central limit theorem and this idea of Z-scores, or standardized scores. If you recall from the central limit theorem, we know that the sample mean is distributed normally, right? It's going to be centered on the population mean mu, and has a variance of the population standard deviation squared divided by the sample size, lowercase n. So that just characterizes the sampling distribution of the sample mean. It's centered on the sampling distribution of the sample mean is centered on the population mean mu, and it has a variance given by the sigma squared divided by lowercase n. All right. Again, in general, we can summarize this as it's just the standard error of the sample mean squared. So that's just from the central limit theorem. Now recall that we can conceive of our sample means in terms of deviations, in terms of Z-scores above and below this population mean mu. So if we just take, assuming that we know the population mean mu, we can just take any particular sample mean, subtract out the population mean mu, and then divide by the standard error of the sample mean, the standard deviation of the sampling distribution. So we're just converting, the idea is we're just converting all these different values of the sample means on the sampling distribution, we're converting them to Z-scores. So they're deviations above and below the population mean mu. So if you get a Z-score of 2, that particular sample mean is going to be 2 standard deviations above this population mean. If you get a Z-score of 0, that sample mean happens to have the same value as the population mean mu. The point is we're just converting our sample means into these deviations above and below the population mean mu. Once we've converted these Z-scores, right, recall that we can create confidence intervals by asking how many Z-scores, in essence, we want to capture with our interval, where these Z-scores are deviations above or below the population mean for our sample means. Right? So the key idea is with a 95% confidence interval, we want to capture 95% of the sample means. Again, these sample means are converted to Z-scores, but the basic idea is that with a Z-star of 0.95, the idea is we want to capture 95% of the sample mean. So this is the standard normal distribution model of the sampling distribution. The sampling distribution is going to be centered on the population mean mu, and it's symmetric, it's mound-shaped, so we can use a standard normal distribution. Now, the area under the curve of this distribution, it gives the probability proportion for a certain range of values. So you can see here that if we set Z star to 1.96, positive and negative, that middle part of the distribution, all right, it captures 95% of all the sample means. Right? So the idea is that when we want a 95% confidence interval, when we want to capture 95% of these sample means, we should set Z star to plus or minus 1.96. Right? That's where we get the approximate 95% confidence interval of 2. Because if we, approximately 2 is pretty close to 1.96, but in actuality, a 95% confidence interval is based on a Z star or critical value of 1.96. Again, when we want to capture 95% of the sample means around the population mean mu, we set z star to 1.96. So we can say that the probability of having a sample mean between negative 1.96 to positive 1.96 is 0.95. That's, you can see the distribution. That's sort of the highest part of the distribution. That's the big chunk of the distribution. That's where most of our sample means lie. That's just from the central limit theorem. Right? The central limit theorem tells us that most of our sample means are going to lie around that population mean mu. Right? But what happens if we want to create a different kind of confidence interval? What happens if we want to create a 99% confidence interval? Well, in that case, we want to capture 99% of the sample means. So if we want to capture 99% of the sample means, right, we want z star values that are farther out in the tails so that we capture more of the sample means in the middle part of the distribution. So we can say that the probability of having a sample mean between negative 2.58 and positive 2.58 is 0.99. So if you want a 99% confidence interval, you should set z star to 2.58. Right? If you set z star to 2.58, you will have a 99% confidence interval because we're capturing, with those two z-score values, right, we're capturing 99% of the sample means. Right? You can see those two goalposts. Most of the sample means are captured. Big chunk in the middle part of the distribution, it's 99%. But sometimes maybe you want an 80% confidence interval. So you want to be 80% confident that the true population parameter lies within a particular interval. Well then, to find that kind of confidence interval, right, you want to find the probability, you want to find z-score values, or these critical values of z star, such that 80% of those sample means are in the middle part of the distribution. So those values of z star, they're going to be closer to the middle part of the distribution because you only want 80% of those sample means around the population mean. So if you set z star to 1.28 and negative 1.28, and you're going to look at that area within those two values, you're going to have a confidence interval that captures 80% of the sample means. To put another way, the probability of having a sample mean between negative 1.28 and positive 1.28 is 0.8. 80% of the sample means are going to lie within that range of the sample means once they're converted to z-scores. Right? The basic idea is that we know the proportion of these sample means, once they're converted to z-scores, that lie within a certain set of values on the sampling distribution. So if we set z star to 1.96, then we know that if you set negative 1.96 to positive 1.96, that middle part is going to be 95%. Right? We're going to capture 95% of the sample means with those two values of z star. We know that these sample means are really just z-scores, so we know that a particular z-score on this standard normal model of the sampling distribution, it's going to equal the sample mean subtracting out the population mean mu divided by the standard error, where the standard error is just as before, sigma divided by the square root of n. The key point is we can plug in this value, all right, of x bar minus mu divided by the standard error. We put it in for the value of this standardized version of the sample mean. All right, so to put another way, we know the probability of having this converted z-score value, all right, of the sample mean between negative 1.96 and positive 1.96 inclusive, it's going to be 0.95. Now we could actually kind of unwrap this probability to actually show where the confidence interval comes from. So we can rearrange with some basic algebra. If we multiply by the standard error, all sides, right, and then we subtract by the sample mean, and then we multiply by -1, so we reverse all this sort of inequalities, then what we have is we actually have the 95% confidence interval, right? We know the probability that the population mean mu, all right, we know there's a 95% chance it is between the sample mean minus 1.96 times the standard error. So the population mean is going to be greater than that. It's going to be less than the sample mean plus 1.96 times the standard error. To put another way, confidence interval is just our point estimate plus or minus 1.96 times the standard error, where 1.96 is based on the standard normal model of the sampling distribution. 95% of our sample means converted to z-scores are going to be within roughly 2 standard deviations of the population mean. To put another way, it's going to be, if you put 1.96 and negative 1.96 and you look at the middle part of that standard normal model for the sampling distribution, 95% of our sample means are going to be within that range. That's where that value of z-star comes from. That's where we kind of can create a confidence interval of any size. Right? If you want an 80% confidence interval, you're going to want a value of z-star that's closer to the middle of that standard normal model for the sampling distribution, because you want to capture 80% of those sample means. With a confidence interval based on a 99% level, you want z-stars that are farther out in the tails, because you want to capture 99% of the sample means around the population mean. So just to recap, the value of z-star, it's based on what proportion of these converted sample means we want to capture with our confidence interval. Right? Again, it's just a point estimate plus or minus z-star times the standard error. The key point is when we set z-star to a larger value, 1.96 versus 2.58. 2.58 is larger. When we set z-star to 2.58 versus 1.96, we're capturing more of these sample means on the sampling distribution. But the thing is, our interval is going to be wider, because the interval is based on the standard error and that value of z-star. Right? The larger the value of z-star, the wider our confidence interval. Right? So to put another way, if we're going to be 99% confident that our true population parameter lies within a confidence interval, that's based on a wider interval. Right? For an 80% confidence interval, that value of z-star is going to be smaller, and that interval estimate, that confidence interval, will be smaller. So the key point for now is to keep in mind that we can calculate confidence intervals of any size by specifying the value of z-star. A true 95% confidence interval is basically the point estimate plus or minus 1.96 times the standard error, but you can also set z-star to other values depending on whether you want to create an 80% or 99% confidence interval or a confidence interval of any size. And with that, we will explore more about how to actually work with confidence intervals of any size.